I had to move on. Now, this is the simulation result. This is the actual measurements. Okay, it's not a radio wave, it's actual measurement. You can see that actually is an energy ball. This is a 0.5 centimeter. This is a 1.5 centimeter. So actually, it is an energy ball of about 1.5 centimeter that we can see here. Okay, now, how does this look like? We can imagine that we drop a stone to a palm. This is a two-dimensional focusing effect. Okay, where is a computer? Who is a computer? The environment. Let's see from system theory point of view. Signal is an impulse we transmit to the channel, and the channel receives a profile or multipass. Time reverse, now we have all this signal. After we transmit this signal through the environment channel, we receive only impulse. What does this mean? The entire room, the environment, is performing deconvolution for us. And this is a perfect deconvolution. It's beautiful. And deconvolution is a very difficult thing to do in practice, including in communication. So this is a perfect. Okay, now let's apply to the first application. Where are you indoor? Remember, we talked about this, the energy ball. This energy ball, we have hundreds and thousands of multipass arrive together at the same time. So what does that mean to us? We prove that when we have so many multipass come together, this energy ball has energy distribution of Bessel function. This is a Bessel function. This is a theory. This is our true experiment. This is a good news because it doesn't matter if this energy ball is collected in India or in US or anywhere in the world. This energy distribution is of Bessel function. Therefore, if at time 0 we are here, in the next time we receive the other channel state information, and it says that the energy distribution is 0.8, and then we know we move this far. So we know the distance. We also know the time. With this, we know the velocity. We can estimate the velocity very accurately. This is dramatic. This is very, very difficult. In fact, we have never been able to do so since 170 years ago when Doppler proposed this Doppler effect. That is for line of sight outside for radar. For indoor, with so many multipass, we don't have any other way to do so. This is excellent. With this, we are able to do indoor tracking. I'm going to show you a video. Hopefully this one can work. I seem to have some technical problem here. Let me try again. Let me restart this. Okay.
Okay. Otherwise, you can directly play the video. If it is not possible from the presentation, you can directly play from the video.
Okay. So let me share again. I hope this time it should work.
Okay.
Okay. In fact, I have so many videos. Without video, it's not easy to appreciate this. So you can see the screen, right?
Yes.
Okay.
In this video, we would like to demonstrate indoor tracking or time reversal. To accomplish indoor tracking, our system uses an origin satellite. The origin satellite is a device that broadcasts a commercial Wi-Fi signal. Using time reversal technology, this Wi-Fi signal is harnessed to track an unlimited amount of tracker bots. With the tracker bot on person, users can navigate themselves with the tablet. Their starting locations are picked up by the origin register. Anytime a bot passes through the origin register, it will automatically start being tracked. There are a couple key advantages of origin systems. Unlike outdoor GPS, requires 3 or 4 satellites, the origin system only requires 1. This satellite can be placed anywhere in an indoor environment. It can cover an area of at least 10,000 square feet. A few other key advantages. Soon, tablets will be replaced by smartphones. And bots will be reduced to the size of a coin. Now for a live video demonstration of Origin's indoor tracking. Here's the Origin satellite, positioned at the center of the floor plan. Here is the Origin register, positioned right outside the door frame. And here is FUNG, demonstrating bot 1. Here is bot 2. As soon as FUNG passes through the origin register, his bot's location is picked up and immediately tracking begins. The second bot can stop and start at any time. Here, you can see both bots being tracked simultaneously on the master command console. At the same time, you can see each bot's location on its own tablet. You can think of these tablets as personal navigation devices that will eventually be replaced by smartphones to help people navigate complex indoor environments. Notice how a bot's path will adjust when it rounds a corner. This is due to Origin Map technology, which allows bots to self-correct for their locations. As you can see, each bot's location is able to be tracked around the entire floor plan with exceptional precision.
You can see that they are navigating themselves, okay? This is in our own lab. So if you ask, this is in our own lab, it doesn't count. So let me show you this. This is in the real demo in Marvell headquarters in San Jose. Their headquarters this is a very big area, 50 meter by 60 meter. It's about 3,000 square meter. We arrived at 9 o'clock. We put our satellite here, and we got a map. We spend 30 minutes process this map. All these are cubicle, and we start to do tracking. I'm going to show you this real data we collect at that time. We do tracking. I want to tell you that we didn't choose the path ourselves. Let's say you follow our employee. Our employee will tell you make a right turn, left turn, U-turn, and go anywhere, okay? And they try to fail us, but they cannot. I'm going to show you next. Now this is the one of it. You can see that there's 2 blue and red one, U-turn, right turn, everywhere. We follow their employee and just do the tracking. This is in their area. This is a very busy area with hundreds of people working there. So this is the first one. The second one, okay. I would like you to pay attention to this one. This one, as you can tell the intention, right? That's to fail us. It worked very well without training. And this go inside the conference room, as you can see. Okay, as you know that this indoor tracking is a 30-year-old problem. Nobody had a good solution, and this is a very good solution. Little or no infrastructure, simple installation, tracking unlimited number of users, because the user is going to look like a GPS you calculate in your device, very high accuracy. Okay, now let's move beyond this. We don't have much time. Breathing. The radio wave impinging on our body when we are breathing. So the breathing signal is in this radio wave, and we are able to pick up the breathing signal. So we conduct an experiment. This is in our lab. We have about a dozen people. We can identify 11 people and pick up 9 correct breathing rate. But this is long ago, okay? And the breathing rate, we can pick it up. What we can do? Sleeping. We can do sleep monitoring. When we are sleeping, you know, every night, we may have 5 to 6 REM, rapid eye movement. What is rapid eye movement? When we have a dream, our eye will move rapidly. That's called rapid eye movement. In order to have a good sleep every night, we have at least 5 or 6 rapid eye movement, okay? So how good is our sleep quality? We have to identify awake, REM, and non-REM. And we are able to do so. We can pick up breathing. We can do motion. We can build an AI analytic to do so. Okay, and we compare with what? We compare with existing technology. There's a matrix, contact matrix, and also radar. This is a radar. It had to shoot directly to you, very close. Our result is the best because the ambient radio wave is everywhere. I'm going to show you a video here. This is one of the Wi-Fi device. This is the other Wi-Fi device. Okay. And then this is our app. Our app. This one pick up motion. This one will pick up the breathing. Okay. So now you can see. We say there's a motion. My people is going to bed. This is in his apartment, in fact. Okay, so we see all this motion, and very soon the breathing is going to be picked up here. It takes 15 seconds to initialize this breathing, this engine to be able to pick up. So you are going to see very soon it come out here. Oh, it start to come out. Okay, so this is his breathing signal. Okay, now we can monitor his sleep quality. Let me move on. Okay, this also has some because I don't have enough time. Okay, now we pick out the breathing. You just see how can we monitor a person? Okay, well-being monitoring. This is elder care facility in Taipei. We have a project with Taipei government. This is the real scenario. This is the bed. We put one sensor here, the other sensor here, one sensor in the bathroom. They say that they want to know the elder person, how many times they go to the bathroom and for how long, okay? So we just put it here. No wearable, no nothing. Then you know what? What we can do? We can monitor the persons with activity. Go to the bathroom, not at home, and then come back. Go to the bathroom, not at home, go out, and then oh, in the afternoon, there is afternoon nap. Okay, this is a REM, right? This is meaning there's a good nap. And then this afternoon activity at night, this about 9:40, go to bed. And with REM, it's a good sleep. And also, not only is good sleep during the sleep, this is the first day, the second day. During the sleep, it's a good sleep, and also get up and go to the restroom. And this is a go out. See, we are able to offer lifelong as a service without any wearable. Okay, now we mentioned we can pick up the speed. We can estimate the speed, right? So we can estimate the speed very accurately. The derivative is these accelerations. These two together, we can decide if it is a 4 or not. Because if it is a 4, the maximum velocity and the change of acceleration is very different from many other different motions. So we can pick up the 4 detection. Let me show you this video. This is a real video we demo to Samsung. They are in Seoul, and they want us to put camera in many different places so we can do demo to them in real time, okay? This is our employee's home, and he is walking. There's no trigger, no false alarm. It's a Wi-Fi. Wi-Fi cover the entire house. Now he fall.
Fall down. Fall down.
Okay?
Fall down.
We detect at this location. Now he's going to the other location in the house. As long as it's covered by Wi-Fi, now it's this location.
Fall down. Fall down.
Okay? So we can pick up this fall down detection. Now, remember, we talked about this time reversal space. So the time reverse, it goes back to the energy ball. If at that moment the door is open, so it goes to this energy ball. If you close a big door, it perturbs the radio wave. It may go to point B. So if we can determine point A and point B, then we will know the door open or not. In fact, the same principle allows us to be able to recognize a person. Yes, we can recognize a person because the radio wave, indeed, we are very different from each other. Not only our face, everywhere we are different. So let me show you this. This is a room without any sensor. And we put one sensor here outside and one sensor here. There's no sensor inside this room. We have about a dozen people. And this is the ROC curve of the recognition rate of these a dozen people, which is excellent. And let me show you this video to recognize the driver. Oop. Okay. There's a noise. This is a hot summer day, very strong wind. This is the one Wi-Fi. Okay. By the way, this is the video we took 3 years ago. Now we are using neural network to do detection. This is second Wi-Fi. There are many Wi-Fi inside a car nowadays. Okay, now Jessica, she is the owner. Now she come to the driver's seat. So now we want to learn who the driver and the owner is. Okay, so we do this now. If you know MATLAB, you can tell this is a MATLAB. Okay, it's very slow. That was about 3 years ago. I don't have a new video to show you, but this is 3 years ago. It's just a proof of concept. Nowadays we use neural network. It is much better. Done. Now it recognizes the driver. Okay. So it's come an intruder. Okay, can we recognize this person as the owner or not? Okay, it is running the MATLAB but still quite fast. Using C now is immediate. Unidentified. Okay, we cannot recognize this person. So how about if Jessica come back? Can we recognize Jessica? Well done, Jessica. Okay, now we recognize Jessica. Okay, I had to move on. I don't want to talk about this too much by using 5G system. It's a 60 gigahertz. We can see the radio. Okay, I want to show you this. Look at this. You see a person, right, like a ghost. There's no camera. This is completely radio, okay? And, okay, now let me stop this. Let's move to the next. In fact, our video quality can be this good. We can penetrate the podium to see the person. This is the optical light. And we can also pick up heartbeat. Let me show you this, okay? You can pick up not just a breathing. Oh, now this radio, the resolution is not good enough, okay? This is breathing rate location, but anyway, let me move on. There's something wrong with this one. With this 5G system, not only we can pick up breathing rate, we can pick up heartbeat. Because we can pick up heartbeat, we can understand and detect the heart rate variability. That is our health index. And we can trace handwriting. You can do handwriting anywhere, okay? Without just with hand, without any special device, we can recognize handwriting. Keystroke, you can type any typing or you play piano. We can know where you pick what is the key that you strike, and with this outstanding recognition rate. And eye blink, when you are driving, we can detect if your eye blink or not, and we can also detect different material using this 60 gigahertz radio. Okay, so what have we seen? We use time reversal physics with all these virtual multi-pass antenna. We can do so many applications. And you know what? By using all these ambient radio waves, we call it wireless AI. Why is wireless AI? Because we make sense of radio waves. Speech recognition makes sense speech signal. Face recognition makes sense image. Computer vision makes sense of video. We make sense this wireless radio. That is indeed a sixth sense to decipher the world. And we have products that can deliver with Lindsay's Aware to about 150 countries all over the world, and we won CES Innovation Award. And this is a book that we publish with the science that we have developed. Okay, I think my time is up, so I will stop here. Thank you very much.
Yeah, thank you, Dr. KJ Relu. You have really delivered a fantastic keynote, I would say. Definitely time is too short for this type of presentation. We would have loved to have at least 1 hour or 1.5 hour of session of yours, but due to paucity of time, we are not able to take it. But definitely very soon we will be arranging an exclusive webinar again on this subject, because we have missed so many important things from your slide. And I can say totally that now with your wireless AI, I am saying all problems are being solved. So there is no problem existing in the world which cannot be solved using your wireless AI. So it is a really commendable job you have done it. And I am really impressed mostly with this older people falling down kind of app what you have developed. And then even breathe analysis, even people are sleeping or walking. So fantastic work. That's what I told. Everything you have done it with your wireless AI. So it is a really commendable job. I will take only 2 questions because already we are 5 minutes late. So first question is, how do the reflection surfaces and orientation such as wall, curtain, and angle of reflection affect the multipath and accuracy of tracking?
Orientation, in fact, the more multipass, the better, okay? So it doesn't matter.
Next question is asked, with all the sensors surrounding us, will it not increase the anxiety of people and increase their stress to be conscious at all times, thinking someone is always monitoring, so we solve one problem and create a new problem?
Okay. New technology come with a new ethical problem. Look at the stem cell research. Look at that we can clone. Indeed, we can create a human being. Okay. So yes, AI. We all know AI comes with a new ethical problem. This one we can use to improve our life, to make the world better, but we have to make good use of it. I agree. There are ethical issues, but this all relate to AI, and we have to address that issue. All new research always come with a new ethical issue. I agree. Yeah.
Yeah, thank you. Thank you very much, Dr. K.J. Relu, for joining us today morning in India. And I know there is evening for you in the US, and delivering a very, very fantastic keynote. Thank you very much.
Thank you. Bye-bye, everybody. Okay.
Bye. So friends, now we will move to our next keynote, which is going to be delivered by Dr. Lance Fung. I will read his brief bio. Emeritus Professor CHUNCHE Lance Fung was trained and worked as a marine radio and electronic officer in Hong Kong during the 70s. He graduated with a BSc degree with first class honors and a ME engineering degree from the University of Wales, UWIST. His PhD degree was awarded by the University of Western Australia with a thesis on artificial intelligence and power system engineering. He was taught at Singapore Polytechnic, Curtin University, and Murdoch University, where he was appointed Emeritus Professor in 2015. His roles have included Associate Dean of Research, Postgraduate Research Director, and Director of the Center for Enterprise Collaborative in Innovation Systems. He has supervised to completion over 31 doctoral students and published over 330 academic articles. His contribution can be viewed at IEEE Explore, ResearchGate, Google Scholar, etc. Lance Fung has been a dedicated volunteer for the IEEE for over 25 years in the various positions in the chapter, West Australia Section, Australia Council, and the Region 10 Executive Committee. Lance continued his research and supervision of the postgraduate students, and his motto is learning has no boundary. His profile is located at this link. We have posted all this bio at our CONECCT website. You can go through and you can access this. So Dr. Lance Fung, floor is yours.
Okay, thank you. So may I share my screen now because, well, it's not enabled.
Yes, now you can share your screen.
Okay, give me a minute. Yeah, good morning and good afternoon and good evening, everyone. I'm just waiting for the screen to come up. Thank you very much for the opportunity today to be among my eminent colleagues. And I must say that, well, the presentation by Professor Liu is really quite eye-opening. Well, although that I have worked on something similar, like the indoor location, but we have been relying on beacons. Unfortunately, the share screen is not coming up. Okay, I'm just still talking a little bit while I'm waiting. Okay, now it's coming up now. Okay, it's share now. But as I said, well, we have also been looking at the problems such as the fault detection, etc. But we have been relying on the video. So is my screen on already?
Yes.
Okay, so now what I do is I take away my camera so I can concentrate on the screen. And I've been using a wearable device as well. So I'm really, well, pleasantly surprised to see that whereby we can detect sleep pattern, well, even without the use of any variables. And okay, coming back to my topic, well, my topic is called recommendation systems. So I would say that, well, looking at the theme of the conference, well, mine is only a very small part of it, well, more on the computer, technology aspect. So this is part of the work that I go join work with my PhD student. So first of all, I must acknowledge the invitation by the General Chair of CONECCT 2020 and the Chair of the Bangalore Section. And I was at the opening last night, and I'm really impressed, well, with all the delegates and also distinguished guests. And well, my colleague is Associate Professor Kevin Kok-Wei Wong. He was my student previously in another university. And also I have a student from Thailand, Suripino. Well, really, this is part of the work from her university, Wellbeing University. Well, the reason I brought it up is quite interesting that, well, they have developed their own library management system. Because one of the issues, well, they have found among they have around 60 or so universities over in Thailand, but they find out that the library, well, management system is pretty expensive. So they develop everything, well, in-house, and then gradually that one is being rolled out, well, to quite a lot of universities being used in Thailand. And then sometimes later, well, they find out that they have so much of the electronic document. So they begin to ask the question, can they really do some further work on that one, look at things like data mining, knowledge discovery, etc. So that's why I come to this part of the research. So it's only a minor part of the overall research. And also this is part of the PhD student of Filipino, and whereby she is also a staff of the School of IT over there. So maybe I just quickly introduce Murdoch University, because I know that the Perth looks like quite remote to most of the people. As a matter of fact, it is the most isolated capital city in the world. And well, in a way, we are on the west coast of Australia. And I know that a lot of you have been to Sydney or the Section Congress in 2017. You could have come over here, but it took you around 5 hours to fly from the east coast to the west coast. But I must say that we have a beautiful landscape. And as a matter of fact, quite interesting that people talk about Black Swan. Well, Black Swan actually is our state, on our state flag. We do have a Black Swan. So this is from the skyline on the Swan River. So our CBD is somewhere in here. So this picture would have taken somewhere around in here, overseeing the other this side. And the Murdoch University is on the south side. We are one of the 4th university in Western Australia. So I'm not going through my personal background, but I would like to highlight the fact that I have also been currently as the chair of the Region 10 Educational Activities Committee, and whereby I do have some projects, and I would really like to participation from sections within Region 10, which I call the Reaching Locals, whereby we want to encourage that the local section to use the local languages to reach out to the non-technical community by using the local languages. And I also been involved in the Conference Quality Committee and also in chairing the Technical Program Integrity Committee. And I also been involved with the NIC, New Initiatives Committee, and also, as you have served in the chapter section and Australian Council as well. So you can also find out my details from my university website. Just simply search profile, Lance FUNG, and Murdoch University. So the content of my talk is I just quickly talk about the recommender system, or also being called recommendation system as well, the challenges we face. And then we look into some of the techniques, the collaborative-based personalization. And also based on this one, they have the collaborative filtering approach and deep learning techniques for the recommendation. And then we take a look at the system evaluation. And then we move on to the collaborative-based personalization in facet selection. And really, this is where the research started, because of looking at the library selections and how to select the document among the Thai documents, and try to do some discussion for the future work as well. So the issue of information overloading. So on one hand, you see in the early presentation that really we have information everywhere. The information come in all kinds of signals. And obviously, Professor Liu's work is really quite earth-breaking, and well, as you can see, it's very comprehensive and very useful in a lot of applications. Well, but on the other hand, we're looking at the availability of all these information and how to handle these. It becomes a problem nowadays. If you do a single search, easy, from the Google, you come back with hundreds of thousands, if not millions. So the question is, how are we going to handle this information? So from the information retrieval point of view, like the search engines, so they can partially solve the issues. So they try to relate something that you are looking for. But then again, there are really no prioritization or personalization. Because we want to do something, the information being come back to you is relevant, and that's what you should look for. So this is where the personalization part comes in. We try to, come up with a system whereby the recommendation, should be something relevant, to the user or the one who's searching for the information. So by doing that, we can reduce the issue of information overloading. So this leads to the needs of these recommender systems. Well, in a way that is already working in the background, no matter you like it or not. Maybe you realize it or not. By itself, it's just simply a subclass of information filtering. So the information filtering, by doing that to address the issue of the information overloading. So by filter out only the important information according to the interest of the user. So if you use a search engine, then what you do is you specify your needs or interests by using some kind of keywords in a query. Well, the recommender system, they are proactive in trying to suggest to use some of these items, they believe to be some kind of potential relevance to the user. And this has been used extensively in the commercial applications. Say, for example, application of the recommendation of the merchandises, entertainment items, online dating systems, social media, and also in academic activities like the search for the research articles, collaborators, or maybe looking for subject experts. So for industrial applications, well, they're actually quite important in particular for business point of view. If you take a look at Netflix, well, they reckon 80% of the movies are being watched came from the recommendations. And YouTube videos, well, they also done a survey, and 60% of those videos being clicked and followed, again, is follow the suggestion from the recommendation. So in the early work, well, it's based on the content-based filtering. So they generally is based on the similarities of the items, which is similar to what you like in the past. So in a way, it makes sense. So comparing what you have, make a record of history of the things that you have selected in the past and try to bring out some similarities. So what it means is, well, you need to set up some kind of a user profile. And also you need to have the information of those items as well. So they try to match it and try to bring forward to you. So the information of the items which are close to the profiles should be will be recommended. So this is what is aimed to do. However, there are some limitations on this approach. First of all, is the information sparseness. Well, what it means is, well, you may not have enough information about the user's interest. Having a cold start is a good example, and particularly, well, there are some unobserved items or queries because some of those have been missed out. And also maybe, well, by doing that, you may miss out the diversity and the novelty as well. Because on one hand, you just try to balance between the two. Well, you try to give you something similar to what you look for, but on the other hand, you also try to introduce some new things to you. So on the other issues, is deriving the interest from their own profile may not be sufficient because, as you can see from the earlier limitations in the previous slide. Well, because maybe the behavior, you get the search goal shift. So maybe the intention, well, they look at some other words, well, they suddenly want to look at some other things. Well, information seeking. So maybe they're looking for new information as well. So this is the one referred to the second point earlier on in terms of the novelty and diversity. So for collaborative-based personalization, the keyword is based on the collaborative. So it's assuming that, well, if there are similar users, so if you have a common items, well, being read by this particular one who try to search for something, and if you can match for someone that's quite similar profile, so we make the assumption that, well, that particular person would have read this. By now, you would have encountered this already. When you look at some merchandise on eBay, Amazon, well, you scroll down the page, and then you will see something like, well, the user who look at this item and also been interested in the other items, then they push to you. This is part of the recommendation system in working. So the other one is collaborative filtering. So this is the most prominent approach in the recommender system. So in a way, well, this is developed based on the collaborative-based personalization approach. So there are two applications. It could be based on ranking, or it could be the top n number of the recommendations, well, of the rank of these of the items. So in here, let's assume that you have a user from UI to UM, and then you have the user item yourself. You have the features characteristics from P1 to P2 to Pn, etc. So you have the intersection, and that they can provide the based on the ranking predictions. Well, based on the user, or maybe based on the item itself. So this is the overview of the collaborative filtering. So there are two ways to look at it. Now, because obviously in terms of the size, well, it could be an issue because in terms of the number of users and the items and the features, etc. So the memory-based collaborative filtering, they use the user similarity is measured based on the nearest neighborhood approach. And the techniques can be used to become a Pearson correlation coefficient, cosine similarity, or the K nearest neighbors approach. The other one is a model-based collaborative filtering. So this one will fit the model from the user item preferences and the prediction. So again, techniques will be like the matrix factorization, like the singular value decomposition, the SVD++, and non-negative matrix factorizations, or the probabilistic matrix factorization. So a number of approaches have been reported in the past. So when you go to deep learning, so we are really referring to make use of the neural network. And well, it has been proven that the deep learning now has been quite widely applied to a lot of disciplines. Well, it has been proven that it is able to address the issues like the sparsity, reduction, cold start, and how to scale scalability as well. So, it has been compared to the other matrix factorization-based techniques. So the techniques being used in here, it could be reduced Boltzmann machines with deep belief network, autoencoder, recurrent neural networks, and convolutional neural network. So in our work, the one I'm going to share right now, actually we have used the autoencoder, then we're using some derivative of it as well. So in terms of the evaluation of the performance, it could be a number of these. It could be based on the accuracy. So it could be the mean absolute errors or the root mean errors. Or it could be based on relevance based metrics, could be precision, recall, F measures, or the normalized discount or cumulative gain. Or maybe cost metrics, just based on the computation time and also the space usage for the memory. So recently, this collaborative personalization has been applied to facet selection. I'm going to explain what does it mean. So this is one of the key processes in dynamic facet search. Well, it's just referred to a hierarchical list of the taxonomies of facets. So they are representing the knowledge, the perspective of the current search. For example, if you're looking for a book, you could under the genre, the author, and the subjects, some examples. So it is an exploration search and currently being used one of the main features in many online retrieval systems. So even we use that in Attribute Explore as well. If you take a look at Explore, we have the facets of author, and then in here you have a number of these values. It could be the name of the persons. Affiliations to be according to the university they're being affiliated with, publication type, etc. So you can see we have already got this one inside our existing system. In Amazon, there's also something similar as well. You've got a facet of cookware, and in here you've got the values, of a number of these choices of the cookware. It could be all kind of pans, skillet, and woks, etc., etc. So if we are doing the facet selection, so what are the challenges in there? But bear in mind that some of the facets are useless or maybe irrelevant to the user's interest. And also the users require some kind of efforts to examine the list. As you can see earlier on, you have to scroll down and find out which is appropriate. And also by estimating the number of facets is also challenging because there are quite a lot of those involved. Because there might be unknown numbers of returned documents and also unexpected queries from the user because of the shift of the goal. So the personalization is required for the list to be adaptive to the personal interest of each individual user. So this is what we're trying to look at. So just like in the case of the Explore, so right now what you see is when someone search, you have the whole list being put on there. So our suggestion is why not you take one step further? Can we personalize the user, and then by doing that, you will filter it already. So the collaborative approach is not only just based on the user, but also based on the other users as well. You've got a whole collections of the user of the common similar interest. By doing that, we can customize and personalize the facets. So the collaborative approach has been one of the most successful techniques using to build the recommender system, as we have seen earlier on. So now, again, we repeat that using the collaborative filtering is the most appropriate technique for building the personalized facet selection. It has been proposed earlier on. So, but on the other hand, they haven't not really go into the personalized facet search. So our aim is, we first of all try to investigate the state of the art or the technique, and then we try to do some experimental work on that. And they are based on the memory base and the model base. And the model base are based on the metrics factorization, and try to get the feedback to represent the user's preference. So the design is, we have the user's feedback, rating between 1 to 5, and but the collaborative filter cannot be applied to it. So we have to prediction at the items level. So, and then when we predict the item at the facet level, the input will be the rating, instead of the user items. So we use the movies lens, which have 100,000 data set. They have around 100,000 of ratings from 671 users based on 9,000 movies or so. So we only select those users that have at least 20 movies where they have dealt with. And then by do that, we look at a number of factors like the genre, the actor, actress, the keywords, production company, etc. So we have the records of the rating to be 10,000, 122,000, etc. So we randomly divide them into 80% for training, 20% for testing. And the metrics we have used, the accuracy of the rating predictions, as we have seen earlier on, can be based on the mean absolute error or the root means squared error. And also the computation time, we want to compare how fast it takes for the training and also for the actual prediction. We perform a 5-fold cross-validation. So we randomize the data, we repeat the experiment 5 times. So we have used a system based on 2.9 gig Core i5 and 8 gig RAM. So we compare 4 factors and we measure by the errors as well. So this is what we have observed. We verify for different genres, and then we'll see how the performance. And then, what you see in here is compare all the different methods in here. Okay, SVD, SVD++, NMF, etc. So on average, what we find out is that the model-based approach will obtain the higher prediction accuracy values, and then the SVD performs one of the best, followed by the other one is SVD++, the NMF, and PMF. So we do recognize the sparseness have influenced the prediction accuracy in the probabilistic approach, and for the memory-based, then we have the K nearest neighborhood will outperform the other comparison. But really, there's not much significant difference between the cosine and the Pearson correlation coefficient. So in terms of the comparing the performance time and also the prediction time, so again, you can see a difference in there. So you can see compare between the memory-based and the model-based. And quite interesting, take a look at some of the SVD++ is pretty long in terms of the training. But of course, now 11 minutes is quite okay. So the results show that the model-based approach obtained the best prediction accuracy, whereas the SVD was the best. And the memory-based methods would spend less time, but due to no training optimization. And also model-based approach to faster prediction time. The collaborative filtering can improve the performance of the personalized facet selection. So that's the first part of the work. Let me take on one step further. Let me look in the neural network. Earlier on, you also heard the Professor Neil mention that they're now using the neural network. And that's similarly, we want to explore further using the deep learning and neural networks. So we want to see how we apply the autoencoder and try to address the issues. So because it has the capability for learning the latent representations and predicting the user preferences by using the content reconstruction technique. So the ideas of the autoencoder is to operate a dimensional reduction, which is similar to the SVD, which is singular vector decomposition. So this is the approach whereby we have the user facet, we have the encoder, which is the network in between, and then we reconstruct the user fixed rating. So there are 2 parts. The encoding part is for the features learning. The decoding part is for restructuring the embedded user facet rating. The parameters we play with are the loss functions, overfitting preventions, and activation functions, and also the model optimizers. So the setup is similar you have seen in terms of hardware. But this time, we not only just based on 100K database, we move on to the 1 mega databases as well. So you can see that, now it's 10 times more in terms of data we're dealing with. We use a similar genres, keywords, actor, actress, and a production company. And we use the same evaluations and also use a ranking and also compare to the other methods. So this is our other comparison. So we also now compare the results, not only just for 100K, but also compare to 1 meg. We have the autoencoder, and also we compare to the model base. So what are the observations we have? We find out that the choice of the parameters using the L2 regularizations, linear activations functions, atom optimizers, we run the 500 times of epochs. And for prediction accuracy, and then the proposed model outperform the comparison collaborative filtering technique. So we see that the autoencoder the model achieved the remarkable results in predicting the interest of the facet genre. The experiments on the 1 meg records produce the results in the same direction as was being done in 100K. So we are quite confident, actually, the approach looks appropriate. In terms of computation time, the autoencoder-based personalization requires much longer training time, but it achieves less time on the facet prediction. So in summary, so this is just a quick short sharing of some of the work that we have done over our side by our student and my colleague. And we just experiment with different combinations, different choices of the architectures and the use of the parameters as well. And then we introduced the autoencoder to implement the personalized effective selection and obtain the highest prediction over the collaborative filtering. And also we compare in terms of time as well. So now we are also working on the other data sets as well. And well, we also see that they have very similar behavior. So we may consider looking at text filtering to improve the prediction of the effects formed by the name entity and the free text. So this is another approach where we are working on right now. We have also other papers, these are all in the pipeline. So but some afterthoughts on this one. So this is really much more general that I know that now lately, because a lot of queries been coming up in terms of the performance of the AI and also even deep learning itself. Example is, well, now it's been proven that, well, some of the system has become a bit biased, well, and that really is some kind of contradiction than what we expect, well, from the ethics. That we do expect, well, our behavior as engineers should not have any discrimination against the race, against the age, well, the gender, etc. But what happens if the system are performing that? So really, there's some kind of challenges we have in hand. So how do we really verify and validate the recommendation? Now, obviously, when I look at the data set, we can say that, well, should I say, okay, we can have accuracy based on this data set. But really, when we look at the unknown, we really do not know. In other words, we really have to rely, well, on the good faith the system is working. Because really, there's no way you can see that what has been recommended to you, well, is really truly, well, unbiased, okay? So we may require some kind of human feedback as an ongoing to check it. And I have mentioned also the ethical issues. Well, I think this is the one that it become very a challenge. Again, I'm really glad to see the IEEE. We have the ethics in action, the website, and then we have publication on that one. We also have a standard, I think, 7,000 on that aspect as well. So I think this is the one that we should promote much more strongly, especially for us dealing with autonomous and AI machine. That no doubt that they are a fantastic investigation in innovation. But then again, we need to really, have a much more comprehensive examination and really how reliable they could be. Okay, and I would say that the research goes on, and that's exactly, what IEEE is doing about we're advancing technology for the benefits, of humanity. Okay, these are some of the references, so I'm not going to bore you with this lot, okay? So thank you very much, and I'm going to stop my sharing now, okay?
Thank you.
Thank you.
Yeah, thank you, Dr. Lance. Thank you very much for an excellent overview about recommendation system, and you have done a lot of work on that, and you have shared the same with us. But we are slightly delayed now, and due to paucity of time, I will not be taking any questions, and I can see a lot of questions are being asked. I request all the participants to directly write to Dr. Lance. His mail ID is available, and better you directly connect with him and get your queries answered. Thank you very much. Now we will be quickly moving to the next speaker, Professor Kathleen Kramer. I will just introduce herself. So Kathleen Kramer is a distinguished lecturer for IEEE Aerospace and Electronic Systems Society, AESS, a professor of electrical engineering at the University of San Diego, CA, USA. She chairs the IEEE Aerospace and Electronic Systems Society Technical Panel on Cybersecurity and is an officer of the San Diego chapter of the IEEE Aerospace Electronic Systems Society. She is an chapter that serves engineers and scientists from a large, diverse, complex system industry base. She is the 2019-2020 IEEE Secretary and Director, and served as the 2017-2018 Director of IEEE Region 6. Her technical interests are in multi-sensor data fusion and application of neural and fuzzy systems to navigation and data security. She received the BS degree in electrical engineering, magna cum laude, with a second major in physics from Loyola Marymount University, and the MS and PhD degrees in electrical engineering from the California Institute of Technology. We are very honored to have you, Kathleen. Floor is yours, and I will make you a presenter. Please go ahead.
Thank you. I'm waiting till it lets me share.
Yeah, you are now a presenter. You can share your screen.
Oh, well, can you see it? It wasn't letting me open.
No, till now we are not able to see your slides.
Okay.
Hope you are having access to share.
Oh, wait. Ah, it's trying to make me quit.
Okay.
Now, perhaps.
Yes, we can see your screen.
Thank you. Well, good morning and good evening, and thanks very much for inviting me to speak. I'm here as a distinguished lecturer for the Aerospace and Electronic Systems Society of IEEE. This is my good friend Walt Downing, who is the 2020 president. And IEEE AESS, we are the first of all the societies. And that's because if you look at the alphabetical list of all the societies, we are first. And so you can always find it and remember. And so we advance total integrated electronic systems and their enabling technologies for complex systems of air, space, sea, and land. I have many slides that I'll just skip through. And at the end, I have my email address. And frankly, I think I'm probably the easiest woman in the world to find my email. But if you just Google, you can find it. And I'm happy to send you a PDF of the slides. And so here's publications. We have a set of things I'm supposed to include, so I've skipped through them. The AESS technical panels. A panel is not like a speaker panel. It's a technical community within the society. And I highlighted 2 of the current 6 panels because I'm the chair of the cybersecurity panel and I'm an active leader on the avionics system panel. My society is probably most well known for radar systems, and arguably we are the radar society as well. But I'm not on that panel, but there is a very exclusive technical community. You have to run and get elected to be on that panel. And we have a mentoring with, if anybody's interested in joining that, we have a mentoring program. And I wanted to also praise my society. We won the IEEE EAB Society Professional Development Award last year. And so on to my actual talk. So feature object extraction is evidence accrual applied for information assurance and other problems. This is just sort of our raison d'etre, our approach to this question is all truths are easy to understand once they're discovered. The point is to discover them. And so as an overview, I'm going to talk about what evidence accrual is, the problem we're trying to solve, the traditional approaches, and then go into this algorithm, feature object extraction, and its use of fuzzy common filters. And then look at 3 applications we've done that use the technique. So in terms of the general problem, as has come up in both of the previous speakers, we're in a network with multiple and redundant sensors that are being used to recognize issues, events, or targets of interest. And the end result is streams of measurement data to sift through, determine which are important, associate which are important and related. And in the end, you're looking to support or disprove hypotheses is one way to look at it. and your goal is a measured understanding and interpretation based upon the measurements. Evidence accrual is the fusing of the information to support various hypotheses. You are accruing evidence that something is true or perhaps that something is not true. And the evidence is perhaps at the atomic level or at the combined level will have a level of impact on what you believe and a likelihood or reliability associated with it. So one question might be, what is the relationship between evidence accrual and big data? And that's just because big data is something that you hear all about, and people are talking about it. And certainly Lance was had an application of it. And in evidence accrual, we're looking to fuse information from disparate data sets and inputs into actionable information and system representation. Well, in big data, you're looking to analyze and systematically extract information or insights from large data sets into an understandable form. And so those are, they're perhaps traveling in the same vehicle, they're families. The major difference is the second bullet in each column, and that the point of evidence accrual is you're updating with each event, and you're trying to develop situational awareness or understanding of what's currently happening. And the big data, it doesn't have to be, but most often you have batch processing in large data sets that you're working with. And the evidence accrual, you're looking for a large-scale picture, and where big data, you have much data, and you're looking to extract values and insights from it. In evidence accrual, we're taking elementary data evidence points and combining them into more complex information. And you could also apply big data into an unstructured, semi-structured data, but the main focus is on unstructured data. But they do sharing, transferring, and visualization are things that they share. So in terms of the typical approaches to evidence and accruing evidence, the most typical approach, and you can look up many people using the approaches to make use of Bayesian probabilities, and very often you graphically express this in what we call a Pearl tree, named after Judah Pearl. And you make use of probability theory, and you assume, you have to make a lot of assumptions, but you use conditional probabilities and combine probabilities conditionally to update your state estimates of what's most likely, and you inject new information into the state. And as you you proceed down to figure out what's going on based on, you'll come to what is the most likely conclusion. And at each level here, our probabilities have to add to 1, and things are either true or not true. So a benefit of this is this is mathematical, and it can be, you know, less mathy. The signal processing type people, we love math, and we're engineers and we love math. And so it's probability based, and you can, and it's nice to have a tree. The drawbacks of it are that it's difficult to really implement for a realistic system. And so you're going to have to make simplifying assumptions about truth, and your evidence and your states based on the information you have, all evidence kind of has to look alike to you. And there's a lot of occasions where you are presuming things to be independent, and they're not. And so you're getting confirmation from what you think are multiple sources, but they're actually all related and dependent data. It's very common to have special heuristics constraints to handle the common, what we call corner cases. And in the end, you will come up with one solution. The notion that you have like a set of probabilities, and that these probabilities have to add to 1, and sometimes things that are very unlikely, you'll just give that a probability of 0, because you cannot have infinity nodes in your tree. And so those are some of the simplifications that people make. And this is probably the most common approach. Dempster-Schaefer is a means of augmenting this approach. And the idea is to add in evidence uncertainty, or how reliable is this reading. So if you had a reading that would indicate event A is happening, but you could factor in that, well, this particular sensor is wrong 10% of the time. And so I don't want to lose that information and count on that I read that sensor correctly that time. And so Dempster-Schaefer allows you to have this quality score on every piece of information. And so the benefits of this is that you still are probability-based, and you can incorporate uncertainty, though, about the evidence. So that's your two great things about it. And you can combine evidence from different sources, and it's very thorough, and you could argue that it's the sledgehammer approach. So the drawbacks of it are that you have to calculate sets of subsets of propositions, all with degrees of uncertainty or probability, highly computationally intensive, and very difficult to implement complex cases. Because you made a lot of simplifying assumptions on when you were doing the Bayesian taxonomy approach, and this puts it on steroids. You essentially, where we had this beautiful simple tree in the previous slide, you basically have a tree for every node of the tree. And so it's computationally prohibitive. The evidence accrual approach being discussed here that you're learning about today is it's a technique originally developed for what's called effects-based operations, EBO. It has a focus on the desired or strategic outcome, not a first-order outcome, not I want to drive the car faster, so speed up the car, but I want to get somewhere. So what do I do with the car? So focus on a non-first order effect and then work back. And it relies upon having an understanding of the system and being able to adapt decision-making rules and assumptions. It is also mathematically based, but much more on the controls estimation side, and it has to incorporate probability, but also fuzziness. And uncertainty and quality of your evidence is incorporated. And so the particular evidence accrual here feature object extraction. So going based upon this EBO effects-based operation approach, so what FOX does, and we call it FOX, is we're going to use I highlighted sort of what are the interesting pieces of it, is that we're going to base it on first order observers, and we're going to have measurements all process, whether they're fuzzy or not fuzzy, they all go through what we call a fuzzy Kalman filter. And so we have a tree structure, and you had a tree structure, and that made it reasonable to do the computations for the case of Bayesian taxonomy. Here I want to point out that while for Bayesian taxonomy, you would typically start and proceed through events and get to the bottom of the tree. Here we're working to the top of the tree. And so we have a tree structure with nodes and links, and levels of evidence are propagated up through the nodes. Each node indicates the state and attribute, and will provide a score that in some ways you could think of as a probability. It is not a probability. It doesn't meet the mathematical specifications of a probability, but there is a score that ranges from 0 to 1, and 1 indicates more of a yes than a 0. And some nodes could be binary, so you could have a 0 or a 1 and think of it as a tripwire. And some nodes are real valued, and they would have measures, and they would be based upon measures of attributes of interest, and they could be combinations of data to get to that evidence. In terms of the very top, so what we're working towards at the very top is an actionable decision or a hypothesis. And so you would have, if you only had two possibilities of what you were looking to decide, yes, I should do X, or no, I shouldn't do X, then you would have essentially two nodes at the top. So very commonly you end up with, say, 4 at the top. And you have competing situations where probabilistically you would say, oh, well, if I have no information at all, it's 1 quarter, 1 quarter, 1 quarter, 1 quarter. The evidence accrual approach, you could end up with high scores on 2 of them because the evidence supports well either of, say, 2 of the 4 possibilities you're looking at, for example. And so both of those could score quite highly, and there would be nothing that required them all. They don't, one becoming more evident doesn't have to take away from the evidentiariness of something else. That's the main difference between probability and evidence accrual. So we have evidence nodes, and they indicate some particular quality of evidence, and I'll show you an example in a moment. And we could have direct measures, and we could have intermediate nodes, though, that are combining those direct measures. So the FOX structure has links, and those direct measures, so the link relationships vary. We could have functions, we could have images, and we could have fuzzy interconnections, like just something being a quality of being fast or big. We have system links that relate the values, and we have measurement links. And any measurement link would have to come through the fuzzy comment filter. And so here's an example of a tree, and this was our first paper that we did applying the FOX, and this was for trying to come up with what was a relative profitability for a sustainable manufacturing application. And so we were looking at the different prices of materials and the processes involved and the byproducts, and giving political scores on how relatively happy and the underlying commodity prices and the environmental impacts. And in the end, you give things do have numbers, but they don't start off with numbers. At each node, you're having a state. And so the first element is the level of evidence of that. And so you could have a high level of evidence that, yes, this is a very reliable measure, or we know this very well, or it's reference information. And then you have supporting states that, based on the observers, those are not coupled to the states. Those are all fed in by the connections. And if you were trying to apply it to your particular application, you would start with the highest node. So the effect, the consequence, the hypothesis state that you're looking for. You create subnodes, each of which has to be where you define what is the evidence you're going to use to say that this is happening or not happening. And then you break it down again and again, however many levels you want to look to combine this data or evidence. So the links are interconnections of the nodes to each other and express essentially what's happening in the state and the map. We use, when we're being careful, we use dashed lines for measurements and solid lines for functions. If you looking at it more mathematically, the tree itself is defining the relationship, but underlying it is this kind of a, the tree is essentially a matrice. You could By default, I think our first application, we always use linear relationships. It doesn't have to be linear, but it just makes your MATLAB run faster. And you end up with a quality score, that Q at the end of the equation on the bottom for the linear or the nonlinear is a quality score. It could perhaps be a poor quality score is a better term, since it's higher if there's more uncertainty about how much quality it has. And you are updating each state based upon its previous state. Our K here, you could think of it as time, but it's really events. And so an event is you receive a new piece of information. And so it could be that and it often is, that you receive new information at each time, but it doesn't have to be relate directly to time. It's event. And so we have a function based upon the existing states of the evidence being fed in. And the Y's here are measurements. And U's are typically 0, but it could be reference information that's being input. So when you incorporate the measurements, so the sensors oftentimes have raw data that don't map directly or cleanly to be injected. For example, radar data, even cleaned up, that's really range-bearing information rather than location. And so you end up injecting with functions into that evidence node, and you have measures with uncertainty on the measures. So people that are into this kind of stuff, and it's almost a joke how it's when you're running a conference and you'll have all these papers from graduate students that'll do a common filter for some reason on their submissions. And so I'll say extended common filter, but it is the workhorse of the Fusion community, as they say. And there's many variations. I gave a talk where I said there's many variations, and I said XKF because there's so many, the variations on particle filtering, et cetera. And then during the talk, somebody was looking up the X common filter, which apparently exists, and that was not my intention to refer to a specific one. I just meant there are many. But in this particular case, we're using something called the fuzzy common filter, which is an extension of the EKF that allows you to have fuzzy measurements. And so here are a set of 5 equations that make up, if you're into common filters, you might have your own variables that you use, but this is the set that I use as a standard part. So we have K is our common gain. Oh, there should be a sub K on it. And sub K here is like with each event that we receive new set of measurements, and we're updating the state based on the last state, and then we're predicting and we're updating, and we're going to have error covariance, and we end up with the maximum likelihood, assuming that we have noisy measurements with Gaussian noise. So if, and everything has to be numbers, they could be numbers, and the noise has to be Gaussian, but we can, we can find certain problems and end up with the data, and we can update our model, and people use this also for system identification. So in the end, the measurements, which in the left column are a set of measurements, so Z are our measurements, and the common filter is a measurement driven. Oh, I better finish up quickly. So, so these are our measurements here, and over here, where we don't have measurements, we have fuzziness, like we're describing something. And so instead, we'll have to take, we can develop membership functions for the fuzziness, like fast means it's going from this to anything above this value means it's fast. And so we end up basically by using moments, we make numerical these fuzzy measurements, and we turn them into something. So for the case where we don't have fuzziness, the fuzzy common filter just becomes the regular common filter. So we looked at 3 different applications: cyber threats, GPS spamming, and tracking. And so here are, I'm going to try to go quickly, I'm running out of time. So we have cyber threats, and you have various protections that you could use. And so one approach is that I'm safer if I just use more and more and more protections. And as we all are using smart devices in the world, we find that it's very annoying to use more and more protections, and you'll just give up and stop using them. So there's how things are designed to be used, and there's how they actually are used. And so you could design versus real use. And so looking at this in terms of trying to use evidence accrual for attacks on these protections. So we looked at if we had a sequential attack, we could set up a tree for that and the evidence for that. And we could look and see whether or not that's happening. And if we could have a parallel attack, and we could have an evidence tree that looks like that for that type of attack, for a non-sequential attack. And we could have all kinds of things that we're looking and observing, so known events, length of time, all these things. So some things we can directly measure and some things that we interpret. And so we built up a Fox system for this particular case. And so all kinds of evidence that we might look at in this case that we would get updates on. And so we did this particular example. And so this is, so we have, in this case, we had four different nodes, but this is just looking at the evidence for one node. And so for one of the, we're looking at whether there was what we call a slow loris attack. And you see that it's looking at the evidence, and then it eventually does start pinging that it has that high evidence. And then here we have the attack where it's comparing, is it a packet attack? Is it a denial of service? Like, which kind of attack is it? And you can see that you could have, unlike the probabilistic system, you could have really no reason to tell whether one type of attack is going on versus another. But you're pretty sure there's an attack, and so both of them are scoring high. Similarly, our next application was GPS denial of service, looking at navigation. And so we look no jamming, instantaneous jamming, jam and reset, or bias buildup. So the no jamming case is just basically there's nothing untoward going on. And we look at all these different evidence and we accrue them. And so similarly, in this case, we looked at jamming versus not jamming, and we deliberately simulated a jamming to see the evidence building up over time. And then, and finally, you can apply this to the common filter itself, not to the fuzzy common filter, but to check on whether you're losing track. And so we did that as well. And so just to, so in conclusion, we presented a different alternative to evidence accrual that is like probability, but not probability. And it's like big data, but it's not big data. And if you had more questions on it, I would welcome those. And here's my email address, but I think I'm very easy to find. And I promise to accept your LinkedIn requests. If you give them in the next 24 hours, I will accept all LinkedIn requests from attendees of CONECCT. Thank you.
Thank you, Dr. Kathleen. So nice of you for generously extending invitation for LinkedIn as well as mail. Yes, as you know, we are already running short of time, so I will not be taking any questions. Sorry for that. And yes, your mail ID is available. I will just read out k.kramer@ieee.org. You can just write your questions to her and she will be more than happy to answer that.
Thank you
So
very
on
much.
behalf of IEEE Bangalore Section and on my own behalf, I would like to thank you for accepting our invitation and delivering a wonderful talk. Thank you very much.
Thank you.
So friends, now we are going to have our last but one keynote. I will be just reading his bio. I see that Nijas is already there. So Dr. Nijas Kunju specializes in RF, antennas, radar, signal integrity, power integrity, and multiphysics simulation. He has been working with ANSYS for the last 4 years. Nijas provides technical assistance for all RF, antenna, radar, especially for driverless cars and 5G MIMO applications. He completed his master's degree in electronic science and his PhD from Cochin University of Science and Technology, Kerala. He has authored more than 20 international and 20 national conference publications. So welcome, Dr. Nijas Kunju. Floor is yours, and you can share your screens.
Yeah, thank you. I can see my share option is still disabled.
Okay, I am enabling. Just 1 second. So participants, we are very happy to inform that ANSYS is our platinum sponsor, and as part of that, Dr. Nijas Kunju is delivering his keynote for 15 minutes. So please be with us. And after that, there will be a poll also. So Mr. Chengappa will be organizing that poll. So please participate in that poll system also. Thank you very much. Yeah, Nijas, over to you.
Yeah. Sorry, the presenter right is not assigned to me so far. Puneet sir? I have some challenge, means the share content option is not enabled. Yeah, I think I got that right. Thank you. Thanks, Puneet Mishra and all CONECCT 2020 teams for giving this opportunity to present the next generation phased array simulation technology with HFSS. So coming into the simulation of high frequency, there are different solvers for different applications. You can say if your geometry is very complex and has a lot of material complexity, you can use FTTD or FEM techniques. If it is wide, a bigger one with a more metallic and in nature, then you can go with a IE or MOM techniques. Even if it is so big, it's like 10,000s of lambda, then you can go with SBR plus kind of technique where the microwave will assume like a rays, shooting and bouncing ray techniques. Okay, and most of the simulation tool nowadays giving the hybridization. What I mean by hybridization is, let's say I have an aircraft here, there is a blade antenna. So in a single design, the blade antenna will be simulated with a FEM simulation. The other part of the aircraft can be simulated with either with a IE or SBR kind of simulation. So all kind of solver can work together in a single design to solve a complex problem. So coming into common steps for numerical simulation, first of all, people will create a CAD geometry, assign material properties, simulation settings, meshing. Once the simulation start, what it will do is it will mesh the complete structure and solving actual equations either in integral or differential form, and then finding the unknown quantities such as electric field, magnetic field, or surface current. So we need to make sure one thing, because the softwares are not solving your CAD model, it's actually solving your mesh. So if you see the right side of this slide, you can see a sphere is meshed with a brick kind of a mesh and a tetrahedra kind of a mesh. So you have to choose a proper mesh as suitable for your structure. Otherwise, your geometry will be nice, but you're not solving the right geometry in the background. Once your simulations are done, you can see how the radiation pattern going to be, how the electric field going to be. The question comes, how to calculate the right mesh for your simulation? Is it a lambda by 5 or lambda by 10 at this working frequency, or is my mesh is enough, or did I overmesh my structure? If I overmesh it, it's going to take a lot of memory and the simulation time in the background. So HFSS came with a technique called adaptive meshing. What it will do is the user has to just create the CAD, then HFSS will start creating mesh, and it will just start to conform the mesh or start improving the mesh quality and making sure that the S parameter will get converged, or there is no S parameter variation between my current mesh and the previous mesh. So that kind of reliability it will check. It will make sure you are going to get a efficient, accurate, and reliable result. So if your mesh is not correct, finally it's everything going to be the accuracy of the simulations always matter with respect to the mesh. Coming into conventional antenna array systems, it consists of power divider, phase shifter, amplifier, then going into antenna array system. So because of the complexity of the antenna array, what people will do is they will divide the problem into different sections, like power divider will be one section, the amplifier, filters, and other things can be different simulation, and in circuit they will combine together. So if you see the block diagram of the complete antenna array, you can divide that into a power divider section, the section where the amplifier phase shifter packaging, then you will simulate your circulator, then finally form everything in circuit along with the antenna array, then you can see the radiation pattern coming out from here. Here we are assuming there is no cross coupling going to happen from power divider to the packaging section or kind of circulator sections. In that assumption, things will work fine. Once you model everything, you can model the complete structure in the software, including power divider, beamforming network, amplifier, then simulate it and see how the field is propagating. Note that the phase shifter amplifiers are nonlinear devices. Still, you need to have a circuit core simulation there. So Maxwell equation will not hold with them nonlinear devices. The problem going to be like, this is one section of an antenna array. If you want to solve such a bigger antenna problem, this is always a big concern in terms of simulation time, memory, hardware requirement. Coming into the finite array domain decomposition, ANSYS introduced this technology sometime back, about 5 to 6 years back. So what it will do is it will mesh the one antenna element. It will create a very fine mesh and duplicating that mesh for creating antenna array. So what is the advantage here is one antenna and the second antenna. These two antennas are identical. So because of the identicality, the field can be coupled very easily. Okay, and then if you solve it, you will see the radiation patterns. The problem with such, the advantage with that one is you can just simulate one antenna and duplicate the mesh everywhere and solve it. You can do the beam steering without simulating it. Each port in the antenna can be individually controlled, means by controlling the magnitude and phases are possible. You can make different shapes of antenna array. The problem with this or limitation to the FFDDM is it supports only one antenna element. And in 5G, you need to have a different antenna element to support the spatial diversity and other things. And it also will not include completely on the radome side of the antenna. The edge of the antennas will not compute in the normal FFDDM technique. So ANSYS came this year with a new technology called a 3D component array. What it will do is this is your antenna array with a radome and everything. That structure can be divided into 4 different things. So as check over here, these 4 different models are completely different. So it will create a mesh for individual things. It will adapt it. But the problem is this mesh is not continuous to the other mesh. So the non-conformal interface of these 2 components is always challenging the computation, and ANSYS break that barrier. So now you can divide your problem into different sections, and finally you can see the first element is replaced every inside of this antenna, and the corners are there, which is the third one, and then you can see the side of the radome, and the fourth one is nothing but the air, which is surrounded by this antenna. You can see this antenna with a normal simulation was taking 92 GB reduced to 18 GB, and the 2-hour 15-minute simulation reduced to just 12 minutes. So much of improvement in the simulation scenario. So this is what actually happening in the background. It will you can divide the problem into different 3D component elements. It will adapt the mesh independently and parallelly, so that you are getting a lot of simulation time improvement in the mesh creations. Once the mesh is created, you can see this mesh is duplicated across the entire area. The antenna element is duplicated across everywhere. So then finally solve it. So this is an example of a 256 elements, means the 64 by 64, 8 by 8 arrays of 4 sections are here. And along with the radome, so you can see this section is nothing but the radome with the curved radome with an antenna. And this antenna is nothing but a patch antenna with so many wires to reduce the coupling between the antenna element. And these antennas can be on the same frequency or different frequency, or same polarization or different polarizations, or totally different things can be happen. So this will take care of all edge effect, multiple element, lattice types. And if you compare the simulation accuracy between the normal simulation 3D component one, the far fields are exactly matching. And over here you can see the meshing time for that antenna was 3 hours 33 minutes, reduced to just 1 hour 40 seconds. And you can see the memory also reduced a lot. 13-hour simulation reduced to 4.5 hours. And if you increase the number of core for simulation, you can see the speed of that simulation. Now you can complete just 1.5 hours in your 60-core machines. And the advantage with another advantage with these computations are you can change your excitations. Okay, you can manipulate excitation without resimulating the structure. You can steer your beam. This is in azimuth and elevation plane. You can steer the beam without resimulating the structure. So one simulation, all the post-processings are in the background. And this is nothing but the coupling between the antenna elements, the port between port 1 and port 2. You can get it in a single window and see where you are getting any spurious coupling between the non-adjacent antenna elements. So another example is, so far we simulated only the antenna elements. Can we simulate with the antenna with the feeding network? So what we did is this is 77 gigahertz antenna. We divide that into 26 individual components and finally form an antenna array, something like this. The advantage is these antennas are repeating multiple places. So if you create a mesh for one antenna, that mesh can be duplicated across the entire thing, and that will speed up the simulation like anything. Over here, you need to notice that the elements are, even though these elements and these elements are totally different, still you can see the field is, this is a spurious field which is going away from this power divider, and that also captured very nicely. The fields are continuous across these sections. That is a one numerical challenge in the background. So over here you can see the simulation comparison between these two techniques. 67% of memory reduction, 37% of simulation time reductions. So same thing for 8 by 8 Vivaldi array. Compare that with the 3D component, reduce the almost like 32 minutes simulation reduced to 5 minutes. So the last slide of my presentation, can we apply this for other applications? So what I did is yesterday night what I did is I just divide one filter into two sections. So this is my actual filter, and over here you can see my filter which was divided into two sections, and then I simulated it. So over here you can see the fields are, the geometries are not the settings for taking the images are not exactly same, but you can see the fields are identical, and over here you can see the simulation S parameters. So this technique can be extended to other applications where the complex problem can be divided into like 5-6 sections. All sections can independently mesh it, adapt it, finally club together and solve it. So simple problem, it actually still you can see the improvement in the simulation time and other thing. That's all from my presentation. I hope I am on time.
Yeah, thank you, Dr. Nijas Kunju. Thank you very much for your nice presentation. And again, on behalf of IEEE Connect, we would like to thank you to be our platinum sponsor. Now we are going to have a small poll which Mr. Chengappa will be conducting based on this analysis presentation. I request all the participants, including panelists, to participate in this poll so that we can have some useful information from all of you. Chengappa, over to you.
So the poll is posted in the QA sections. You can have a look.
Dr. Niju, it would be available to the participants. I see them responding to it. So we would be sharing the results post this. Yeah.
So Chengappa, can you just do this polling?
Yes, sir. It is pretty simple. So the attendees who have joined would be already. I see that they are filling in the polls. I am seeing the graph moving. So post this, we would be sharing the results with answers. Yeah. Depending on what response we get.
Yeah. I think all attendees please participate in the poll so that we can quickly finish this. So again, I request all the participants, please complete the poll so that we can go to the next session. I can still see a few of you have not yet started. I think Chingappa, time is over. So it shows that remaining time is 0 minutes, so we can go to the next session.
Yes, sir. Yes, yeah. So yeah, we have the responses received, so we can share with them.
Okay, thank you. So friends, now we are going to have our last keynote, which is going to be delivered by Professor Devrata Das. So I will just read out his brief bio. Devrata Das is serving as professor at IIIT Bangalore. Before joining IIIT-B, he has served at G.S. Sanyali School of Telecommunication at IIT Kharagpur and later at Kirana Networks in New Jersey, USA. He is co-PI of a project from Ministry of Electronics and Information Technology, Government of India, and Cognizant Technologies Limited on a smart home, and PI of a project on network reliability, Tejas Networks. He was PI of multiple sponsored projects from Intel, HP, Microsoft, Motorola, Cisco, Nokia, Government of India on areas of broadband, wireless, Mac, QoS, energy saving, IMS, TVWS. His main area of research interest are Mac protocols in wireless access network, QoS, power saving. He has more than 150 peer-reviewed papers in different transactions, journals, and international conferences. He has 3 patents and 10 more are under review. Dr. Das received his degree from IIT Kharagpur. He has received Professor K. Srinivasan Memorial Award 2017 for excellent teaching in the area of telecommunication from IEEE. Dr. Das has received Global IEEE MGA Achievement Award 2012 and Outstanding Volunteer Award 2018 from IEEE Bangalore Section. He is Fellow of IETE, Fellow of IE, Senior Member IEEE. He was a recipient of HP Endowment Chair Professorship in IIIT-B from 2003 to 8, 2010 to 12, and 14 to 17. He was chairman of IEEE Bangalore Section in 2017. He is a board member of IIIT Bhubaneswar, Technical and Empower Committee of member of e-governance from Government of Karnataka. Dr. Das was the Dean Academic and R&D at IIIT Bangalore. I would also like to add, which is not written in this bio, Dr. Das was founding member of IEEE CONECCT. So still he is our steering committee member, and he is guiding force for all of us. And credit goes to him in making the stature of Connect to such a high level. So welcome, good morning, sir. We are very honored to have you. Floor is yours.
Good morning. Very good morning. Can you please activate sharing?
Yes,
Thank you very much, and I'm really
yes.
thankful to Mr. Puneet, General Chair of IEEE Connect, taking it to the next height. Very big now. Connect is so nice of him and his team, and I can see the galaxy of speakers from different part of the world. It is now a truly international. Great. Thank you, Mr. Puneet, for inviting.
Yes, sir. Now you can share your slides. You are a presenter.
Thank you. Are you able to see my slide?
Yes, we are able to see you.
Great. Thank you. My voice is clear, I hope. So, very good morning, all the participants, and welcome to IEEE Connect. And this is the talk which we are giving in Bangalore Sections first time in the area of 6G. And let me tell you very clearly that it is which take at least 10 years to come and deploy it. As you know, 5G is getting deployed only a few months last year onwards in a bigger way. However, the 5G's multiple things are yet to be developed and also tested. And those who are hardcore in engineering, developing all these base stations and user equipments, IoT devices related to the 5G, they know how much work is yet left and how much hard work is yet to be done till it stabilizes and also it attains all the requirements of the standard. So it will take another 3-4 years for 5G to, but as you know, the whole world always looks at the advanced problems which may come, and they have started discussing on this. So in that respect, I want to talk about a few why 6G and the major challenges people are envisioning and started working a little bit on this direction across the globe. And to be particular, I'll be talking on medium access control protocol and a couple of solutions which we are now addressing in our labs. I also want to thank, before I go into two of my lab mates who have contributed to help me to make these labs, Tushar and Sharvari Ravindran, for this. So this will be my overview of my presentation. Quickly, I will recap on the 5G, which I said, and the 5G's limitation with respect to the futuristic applications people are talking about. Input of key points in the first 6G summit, which happened, and also there are top labs in the world, and also some academicians also presented there from the standard body. Also there, they also presented. One of them was from the IEEE. So inputs from the key points from that research, and some research papers have started coming in different conferences, top conferences and publications 6G. And there are multiple areas in the 6G. I'll be focusing a bit on aerial communication, which people are taking it to the 6G standards and some problems, and the summary, some key focus areas of research we are thinking in the medium access control protocol. And most of my slides and the below, you will find a reference added in each slide, so you can find in the below. So path beyond 5G. As you know, you can look up that emergence of 5G and 5G services, and 3GPP release 14, 15, and 16, and 16 is yet to be finalized, and people are talking about by end of this year may be finalized. Some are talking about the mid of this year, or some because of the COVID, it may go down to the end of this year. So 5G new radio IMT 2020 specification for non-standalone and standalone operation or for 5G networks. So if you look at the 5G has mainly covered three broad areas of the services, like massive machine type communications, and there are a lot of IoTs are coming in, and they will be distributed across they're expecting 200,000 of IoT devices over square kilometers, And I think it is possible, because if you look at a dense city like Delhi or Bombay and some extent Bangalore, in 1 square kilometer we have smart meters of say 20,000 houses are there. So in 20,000 houses, every house, because of the flats and all, we have multiple houses. So every smart meter is an IoT device. So along with that, there are so many IoT components will be there. And next is your enhanced mobile broadband. People are talking about downlink and uplink in the 5G, 20 Gbps and 10 Gbps. Ultra reliable low latency communication, which as people are talking about 1 millisecond. However, these kind of things we know how difficult to achieve with respect to technology, because we moved from 4G, then 4G advanced, then now into the 5G, and in the 5G getting a 1 millisecond delay with so many types of things, particularly in case of handoff, particularly in case of registration to the network, those RACH procedures, random access channel kind of procedures. So this takes time. So achieving this is a big challenge. However, now people are thinking that fourth industrial revolution, which people made a part of the 5G, they have taken that revolution or the evolution of the fourth industrial revolution to a next level of requirements, where the people are thinking in the world this 5G may not meet all those things. So they are bringing those requirements to the 6G first. Then they are setting up these numbers. What will be these numbers for the 6G? From there, the research areas, what should we address and all. So this is the flow of my talk from 5G. So as you know, 5G has achieved a lot of things. If you look at the key technologies which 5G gave us is the new spectrum efficiency under that, 5G core, new kind of core elements, their functionalities, and also according to the new requirements which we discussed in the previous slide, these three requirements, and inside each one of them, each IoT devices or multiple IoT devices, different requirements. For an example, a medical IoT device has emergency requirement of delay of say 10 milliseconds, whereas other IoT devices like metering will have a half an hour or 1 hour of transmission delays between two transmissions. So there are for different requirements. So there was network slicing concept came in to the 5G in a big way, because it is possible now because of the RAN virtualization and the core virtualization. Both are possible now, the radio access network virtualization and 5G core. So this virtualization as visible at here, according to your massive IoT, enhanced mobile things and ultra reliable latency, you can make the machines virtualized. How much CPU you need, how much memory you need, how much spectrum you need, and all those things calculated and optimized according to your applications. And this leads to network slicing. Softwareizations, because multiple new applications coming in, how quickly we can change the base stations and support these applications in a UE, that is possible. And also those core networks devices or elements, quickly I have to support them by changing their softwares according to applications. Beamforming, massive MIMO, and multi-connectivity. These are the concepts happened, which was evolving from, of course, 4G advanced, but that went to the different level of latency, different level of throughput, different level of handoff and delays, and all those things possible because of this virtualization, optimization, and network slicing. So this leads to a very ambitious. Still, I said your 5G is yet to be completely deployed and enjoyed by the citizens of the world. But as you know, with the scientific community doesn't sit quiet. They went on thinking in the first 6G wireless summit, and they came out with multiple requirements. And these requirements are very, very practical, looks like. Why? Because of bringing in industry into the network in a more larger way and more bigger way. For an example, I'll tell you till 4G, if you look at your mobile handsets, it was used majorly by the we people. Means that for our voice calls, video calls, some extent games, mobility, and multiple financing things, and 4G advanced, which we are using now, LTE and all. But 5G brought in the industry into it. They said that fourth evolution of industry has to come in. But look at 4G was ICT, I mean information communication technology. 5G brings in industry. But industry has a huge range from, if you look at the industrial requirements, a huge range, particularly if you look at those robotics and also there then comes the control of the arms, and where the precise of the delay has gone down further from 5G's requirement. 5G said 1 millisecond, they are telling no, we need it a fraction of 1 millisecond for this control and communication between the industrial requirements. So those kind of requirements came in. So those requirements came in due to following things. So if I went, those are, if you look at some of the presentations of this first 6G wireless summit, then they're saying by 2020 to 20, because I say 6G will come around 2030, so there will be 80% increment in your mobile traffic. Now it is in 62 exabyte, it will be 5016 exabyte. These are the predictions. And out of this, there will be 75% here will be from videos. Okay. And these videos, which is why it will be so much high, you look at this. We are now having 2K or 4K televisions. And now for this one, good quality of 2K to 4K, I need 1 Gbps wireless communication. Okay, this calculation. So if I go to 8K, then this is called super high density vision TVs. You can see the quality here. This is going to be 256 gigabits per second to the TV only. So that means I need above this communication in my home from my access point or base stations, small cell base stations to my TV only, one TV. If you have 2-3 TVs at home, say you have a grandparents, you yourself, your parents, and all, so then 3 TVs, children wants also another TV and games. So you can imagine how much you need in this 256 multiplied by that number. So these kind of things people are predicting down the line may happen if this intensity or the density increases. Along with that, people are talking about hologram 1 gigabyte per centimeter cube. I'll give you an example. You see, this COVID has taught us a lot of excellent things. One of the things is that the distance education. Our engineering educations, particularly computer science and part happens a lot of by slides and all. But think about an electronics engineer. Think about a doctor. His classes, MBBS classes is happening. He has to see a body and the cadaver for his MBBS class called anatomy. So 3D holograms of the bodies has to be done. So he can see internally where the nerves are going or all these arteries and all. So those kind of education hologram of centimeter cube, 1 centimeter cube needs 1 gigabyte of transmissions. And it has to go on streaming continuously sitting at home and somebody is taking class. And so many students across the India or the world having streaming. So you look at the bandwidth and the no delay kind of or minimum delay and super SD kind of things. So super immersive multimedia. I'm simple example I'm giving from the education. There are so many other entertainment, all kind of things are there you can think of. So these are kind of applications people are thinking and coming, and plus with the precision, control, and delay, very low delays. So these are the things people are pushing towards 6G. In that respect, this was from the Samsung Research Lab, the slides, then this is on the Nokia Bell Labs. They are now Bell Labs. So there was a thing which is very interesting. They're talking about the capacity, and also this capacity has three triangle: efficiency, space, and also the spectrum. And this capacity building by how this one is going to help in reliability and latency. Why reliability is more required? Because in the wireless, as you know, even though I have a 99 point, say very close to, I'm sitting to the access point, my reliability is 99 some 7, 8 or 9, but they need after 99.9, 4 digit of 0.999 like kind of reliability in case of automation inside a plant. No loss packets, no information. So same information in the space has to go to one destination in a multi-path. So this kind of thing is people are thinking of. So channel redundancies for that, robust modulations, latency. I told you it is less than a milliseconds. For an example, this synchronization of the networks. Previously, we are thinking of, if you look at release 16 of 3GPP, the synchronization time was around the 1 microsecond or like that. But now people are telling it has to be sub-nanoseconds. It's a huge number of times, from 1,000 times. So it's not easy to do that. Those kind of networks, synchronization between multiple heterogeneous networks, synchronization between the user and the IoT devices with the network. So these are the things people are thinking under the sixth. And the very interesting concepts they are also coming in is that sometimes while talking to our friends and colleagues, we say, hey, my sixth sense was thinking like sixth sense, we say, use that. So, but that comes once in a few days or a month, sometimes we say, and if that is also a probability, sixth sense may be right, sixth sense may be wrong. Most of the times, if it is right, then we speak, oh, my sixth sense was saying. When it is right, when it is wrong, we remain quiet. But look at, even inside the body and mind, if our sixth sense is working, but we are not able to conceptualize what exactly it is. So I need to augment my intelligence, human systems. So augmentation by reading our thought process, reading our intelligence, reading our predictions, which we called as artificial intelligence, but we have to take it to the next level of sensing, that is called human sense and human systems, where huge computation, huge thinking of AI has to come in, and it has to be very fast, augmenting your digital nervous systems, digital thinking, all kind of things to help a human being to have a more comfortable of life. So these kind of things that people are talking about. Then there is another presentation which came from the Orange called EMF. So they have all the kind of things, but one of the things they're talking about electromagnetic functions, which will definitely talking about that how these electromagnetic radiations will affect the body if so many things are there. That is an interesting thing, ML for the wireless. In that, they are talking about that, as we know, all your devices, mobile handsets will send the data to a data center where there will be classical artificial intelligence will be there. He will giving you command. But it needs, there will be delay, there will be other kind of challenges. But overcome that, they are talking about collaborative AI. That means there will be no cloud at all. These mobile devices will have the intelligence. This is called edge computing. Some of the companies in Bangalore also working. And my mobile devices is now quad cores, 8 cores, so many RAMs and all. They will do the intelligence and they will share among themselves, keeping the privacy intact. That is the multi-computational secrecy kind of things comes in, and immediately the communication will happen and everybody will come to know what to be done, what not to be done, the collaborative AI. Here, there is no cloud. That is completely things are done in a distributed way. But there is a third dimension to it called federated AI. In the federated AI, these EVs will do the computation of your intelligence things requirement. A part of it will go to the cloud, not full, because these are the practical usage of your say driverless car. If a driverless car, the car itself is like a mini cloud along with a huge computation. And everything he may not able to do all those computations, he will send to a nearby edge computing or cloud. All the cars will send some part of this computation, and this fellow will compute and tell, hey, whether to drive, not to drive, all the environmental conditions, and car-to-car communication, informing to the others and all. So these kind of things may come in called federated AI, these examples. The first one we know, second one is coming up, but third one is going to sustain because of integrated kind of things. But for this, we know the first one, what happens, we send the data from here the communication. So this machine learning communication, that is called. We communicate for the machine to learn the cloud and come back. But the next one is that communication for ML, CML. These are new concepts this paper talking about, that you communicate the data to for the machine learning and the reverse with new concepts people are talking about. So in that respect, so in brief, if I look at in brief, the 6G revolution, wireless evolution from the connected intelligence things to the network softwareization, which happens to network intelligentization. So that means network itself will be intelligent enough to tell you what to do, what not to do, how to do to the industrial IoT devices to human beings. So this will be a big shift, which will expect to the sixth sense, or the example I gave and other examples of this previous slide I gave from taking the references. So now with respect to that, if you look at, so new requirements have following things. This red one is our 5G. But if you look at different dimensions, 6G has gone one step. One couple of things I will tell here is look at this. Latency was 1 millisecond at here in the 5G. Now they are talking about 0.01 to zero point 0.1 milliseconds. So that is going to in your microseconds level. So mobility, 1,000 kilometers per hour, spectrum efficiency, and all those things in 6G people are expecting to giving the previous examples, use cases supports. So ultimately, what is the things the people are talking about is this, that the convergence of communication, control, computing, localization, and sensing will happen. This is called 3CLS in 6G. That means communication part you know, but control part individually you know, which was not there in our ICT world. But operation technology in the industry has brought in this control. So the control and operation technology computing of those microsecond, nanosecond level of delays, accuracy, high reliable, ultra reliability, more the URLs is there in 5G, but much above that, all those things are coming in. And localization, exactly precisely where to keep the things and sensing. So these kind of things has all kind of traffic, dynamic traffic problems and flexibility, deployments, but the infrastructure, same network, same base station, same medium and all, how to avail this. This is the challenge. So with respect to this, these are the 6G's areas like aerial communication, terahertz communication, AI wireless, EMRL communication, user-centric, service-centric architectures. All these are the bullet points that in the 6G people are now talking about and already started putting those points. So I'll be a little bit focusing on aerial communication with respect to 6G because in the 6G, one part is in 5G it is there, but the other part is in the 6G that top people are talking about. So why aerial communication? You know, the stadium, there are so many people sitting around, and if you look at them, they suddenly once in a Chinnaswamy Stadium there will be IPL match or a test match, one day match, huge populations. And that population, for that, if I put the base station, everything, but I'll not get revenue whole the year for a 3 hours match or a 6 hours match per once or twice in a year. So for that, for how to augment this our terrestrial networks. So people are thinking about in this kind of traffic jam, which is very common to us before COVID. Thanks to COVID, now we don't have this, but you look at many times we have a call drop while we are in congestions on the outer ring road sites. So these kind of time, if I can fly a drone or a low altitude platforms on these places, I can cater to these users. So these kind of things are coming under the 6G. So there are so many examples you can see at here. People are talking about what example I gave you in the previous slide, a civilian, but there are some examples of the war scenarios. If your base station is other side of the mountain and your army is mounting on this side of the mountain, you now watch in the TV and all the Himalayas where our army are and all. And if you have worked a little bit, I have on the defense networks and on, you will see how the defense networks opens up, collapse. They're like a collapsible gate. As you proceed forward to the territory of marching forward to the enemy, this networks like a collapsible gate, it opens up. Opens up means there will be a base station at the in your territory, and this one will open up by connecting different nodes on a vehicle. And this one will be connecting to the soldiers. But if there is mountains and this vehicle cannot move, so I have to fly this one and connect. So all these kind of things are coming up. This is called UAV classification. This has two kinds of, one is high altitude platform and another is called low altitude platform. So we are more keen towards low altitude platform in our studies because it is cost effective and management will be easy. Okay. But high altitude platform communications are there under the called as a non-terrestrial networks kind of communications. So in this regard, we did a lot of survey on aerial communications and deployment on the lab-based drone cells in challenging different constraints, load different results. And for actual deployment and the use cases, we found out that important aspect of user experience is missing in till now available all these low altitude platforms called drones communications. So we studied a lot. We found out that there is which I'll tell you in the next slide, that what part is missing for user experience. That means if I put a low altitude platform and thinking that user equipment below that will be get benefited, yes, they may get benefited, but they may not get the maximum throughput or maximum utilization of the spectrum, because the drone is not optimally positioned with respect to the user equipment or the mobile handset. So then we did another very interesting study also. See, the drone or low altitude platforms are battery operated. So there are a lot of work has been done on how to replace the drone if the battery goes down. Many sets of papers say bring down the drone again and change the battery quickly. Like you have seen the racing car, they change the tires quickly. So change the battery quickly and fly it back. Or you fly a new drone to the that place, bring down the battery down. So, but this takes time, and moreover that the communications going through the drone, when you bring down the drone and put a new drone to that position, the sessions get disconnected, and again you have to reconnect the sessions through the new drone. That takes over time. So we completely make it close to zero by a new technology called drone cloning, which I'll talk to you. These two things I'll talk to you. So now these are the two types of standalone augmentation of the drone. One called standalone, where you can see terrestrial networks communicates to the drone and drone communicates to you. But we are more interested in augmented technology, where this UV was connected directly to the base station. But if this signal is low or performance is not good, then it goes to through the drone to the here. So we majorly talking about that. That means my UV is always inside the terrestrial network's boundary. That means if this is a terrestrial network boundary, inside these dotted lines are my drone's small coverage area. If my particular UV is not getting a good coverage or good bandwidth, the drone has to be positioned there. So where to be positioned? If you look at this drone has a three dimension: x-axis, y-axis, and z-axis. So exact positioning on a drone, what algorithm I should use, then my UV at here will get a maximum throughput. So for that we came out with these are all the literature survey for those kind of problems. I am just showing you that this problem is talking about optimal altitude to find out where the drone should be. This is called efficient deployment of multiple unmanned aerial vehicles in the networks of optimal wireless coverage. And this is from wireless communication letter IEEE. This is from SPA-WC IEEE, where it is talking about joint design of 3D positioning of lab-based successive convex optimization by these solar drones. Okay, but in the night it will not work. That is a problem. And these are the multiple drones are there, which one to fly, which one to bring back, and this is a cluster of drones. This is a contribution of this paper. Using mobile, there are multiple papers which have been talking different issues, but they have missed that positioning of the drone, which we have addressed at here. So optimal positioning of trajectory drone networks. So you can see here this drone. There are 4 parameters which we gave a proposal called feedback from EU to terrestrial network. Define feedback for aerial and cell trajectory called FAT. So feedback for aerial cell trajectory, and this select the UV's higher resource requirement, poor channel quality indicators for serving the terrestrial cell stay static for the next aerial scheduling period, ASP. So we found out how much time this drone will be remain in the ASP, and these are the 4 parameters which is communicated from EV to the terrestrial base station. According to the terrestrial base station calculates that what should be the position of the drone and inform the drone, and drone optimally stays there. So those parameters are predict buffer uplink and downlink, and prioritization of traffic type, probability of staying in the same zone for the next ASP, aerial scheduling period, and channel quality measurements. And this gave us a wonderful result. We can see here by using LSTM kind of thing, long short memories. This one we got around 44% of improvement in our proposal for the bandwidth utilizations. So these are so every contribution by the others also, and you also will lead to this, as you know, in the research world, for a better tomorrow. So this is one of them. And second problem is how I said is the aerial cell cloning protocols. That means if this drone is in the red, already battery is down, and I will bring it down, but all the sessions going through will be get disconnected. So if I bring another high powered drone, I'll exactly bring it close to the same location. And how intelligently I'll transfer the sessions going on to the new drone before I bring it down. Then there will be no disconnection of the sessions. There will be no delay for handing over. So these concepts has been given in this called ACC. We call it called aerial cell cloning protocol. The aerial cell cloning ACC protocol, which is being explained at here, which you can see this dotted line is our contribution. Is inside this dotted line. You see this is the aerial energy level status, dispatch of the aerial cell request, dispatch of the location request and all, and dispatch of location city. These are there all before, and this is the now when I get the proximity link request, proximity link links setup conference, proximity link conforms, then the aerial context transfers. So from the old, the new, all the aerial context got transferred, and then the handover happens. So this UV will not come to know so quickly. It will happen close to zero, very close to zero latency, very close to it. And this is a ratchless handover. And we found it is only 20 millisecond delay, where previously it was 60 milliseconds. So I am almost done. I'm only 1 minute. I'll speak. I'll only speak on done. So these are the things done. So aerial research, additional research problems in 6G MAC. If you can look at, this is 3D networking. So 6G communication in 3D space across different propagations environment. So you see, many people of us know about those spectrums and physical layer and all kind of things. And many people work there also, very good works people do. But there above the physical layer, there is something called MAC, medium access control protocol. So different applications, when the packet comes in, that now we used to do 2D, but now 3D space, how to schedule those information efficiently. So those kind of research problems are coming in. So the scheduling would require a new network design due to complexity of resource management 3D networks. So these are the complex problems will come in. And my last slide will be the design of AI-driven scheduling and coordination and signaling mechanism that do not require predetermined and rigid frame structures compared to the 5G. Development of adaptive multiple access protocols that can dynamically change type of multiple access depending on applications needs as the requirements are delays and throughputs are changing. Developing new authentication identification, because this authentication identification takes time. So we have to reduce because our delay to reduce. Design distributed edge AI inspired protocols for 6G functions. I told you about the driverless cars. So those kind of things, how to do that. ML for communication, therefore now the communication for ML, how to do that. And these are the references, and you can go through, and a lot of research already started across the globe, just started a few on your back. So, and thank you very much for giving me this opportunity. This first time in our Bangalore Section and CONECCT, we are talking about the 6Gs as a keynote. I know along about 10 years from now. So thank you, Mr. Puneet. Over to you.
Yeah. Thank you very much, sir, for presenting a very, very futuristic topic. So I think we invite you to block your date for 2030 CONECCT, when we will be having real 6G and you will be again giving a talk on 6G implementation. So please block your calendar, and we will be really happy to have you again at CONECCT 2030.
Thank you. At that time, all the younger generation will come and give you the test bed. We'll be there. We'll be there. Most like that.
Sure. Yeah.
Thank you.
Actually, from 11 o'clock, we are supposed to start our technical sessions. So there will be 5 parallel technical sessions. So we really don't have time for any questions answered. So I request all the attendees, if you are having any questions, I can see few questions are there. His mail ID is d.das@iitb.ac.in. You can reach out to him. He is very well-known person. I know that he will respond also very quickly. Thank you very much. And with this, we have completed July 3rd morning keynotes, where we had 5 very, very distinguished speakers, starting from KJ Relu to Dr. Lance Fung to Professor Kathleen Kramer, then Nijas Kunju, and at the end we heard just now Dr. Debrata Das. So thanks to all the keynote speakers on behalf of IEEE Bangalore section, and on my own behalf, our heartfelt thanks are to you. Thank you very much for joining us, and attendees, please join your respective tracks and start making your presentations. Thank you.
Thank you, everyone. Namaste.
Thank you.
Bye,
Sir.
Puneet.
Namaste.
Bye, Mr. Have a nice day. See you.
Bye bye, sir. See you. Yeah.
See you.
See
Bye.
you, sir.